Good morning, everyone. My name is Boyang. I'll be introducing our work on model information stealing from scientific plots, which is a collaboration between CISPA, NetApp, and University of Virginia. So as we are all now familiar, although machine learning model has shown promising performance across multiple fields, it is becoming more expensive to train them. So during the model development process, to find the best performing models, engineers and researchers usually use their expert knowledge and spend hours searching and testing the best architecture and hyperparameter settings. As the model become more and more expensive to train, these model information is valuable assets of the model owner. There indeed has been some previous work successfully steal these hyperparameters or information to create clone models of the target model. And these attacks typically first use a data set with similar distribution to query the target machine learning model and obtain the responses. Then, so using these query response pairs to train an attack model, aiming to extract the original model's information. However, since these attacks, they rely on query responses of the target model, it can be detected and alert the model owner or mitigate by perturbing the output of the model. So we're curious to see if there exists any other channels that are typically not output dependent for this model information attack. So if we take a step back and look at a typical machine learning model development pipeline, we notice that scientific plot is an indispensable tool to provide high-level representations of model performance without giving direct access to the model. And as a result, they're typically considered as safe. Here we give two examples. One of them is TSNE plot or TSNE plots. This is a popular method that maps high-dimensional embeddings to low dimension, usually 2 or 3, for visualization. Can be used to represent how well the model can generate features to describe and classify the data. And another popular plot used by the community is loss trajectory during the training process. It can be used to showcase useful information such as overfitting level, how well or how stable the model converges. And these plots are a direct reflection of the model behaviors. However, since the information is usually compressed, they're not considered as sensitive information and widely used to present results by both industry and in academia. For instance, you can expect to see them in a paper or just a blog post. So in our work, we aim to exploit the information leaked from the scientific plots to infer model architecture and hyperparameters of the original model. And I'll give an overview of our attack process. Overall, the attack is quite straightforward and simple. We also make some assumptions about adversary's knowledge. So the adversary, of course, has access to the target plot. Similar to previous work, we also assume the adversary has have some data from the same distribution as a target model's training set, as well as possible candidates for the target hyperparameters or architectures just by making educated guesses. So the attack consists of 3 stages. Using the auxiliary data, we first train multiple shadow models, each model with architecture or hyperparameter settings randomly selected from the pool of possible values. So in the second stage, we use the shadow models that were trained to generate corresponding plots that resemble the observation as closely as possible, just by choosing appropriate settings, such as axes, colors, marker size, and etc. So this provides us with pairs of model information and their corresponding scientific plots. And then we can use these information and plot pairs. We can train an attack model that is essentially an image classifier that uses scientific plots as input and predict information of the original model that generated the plots. Finally, at inference time, we just input the observed plot into the attack model to extract the target model's information. And now I'll present some of the results we find First, we'll take a look at inferring model information from t-SNE plots, given the target model uses a popular architecture such as ResNet or VGG. So our results show that the attack can successfully extract the model type, batch size, and optimization algorithms from the target image classifier that are trained on 3 different data sets. So if we assume a strong adversary who has knowledge on all model information except for the inference target, and the attack accuracy is presented in the parentheses, we can see the attack can achieve extremely high accuracy. So while attack model using popular architectures can be similar if they're from the same family, for instance, ResNet 18 versus 34, but the models are still quite different from each other. So we want to explore to see how our attack performs with more fine-grained settings. So building custom models allow us to test the attack model's performance on 6 additional inference targets, as you can see here. And our attack can still succeed on multiple targets, such as activation function, the number of fully connected layers, or the number of convolution layers. And these tend to be the ones that have greater effect on the model's behavior and performance. However, the attack on some of the other targets remain relatively close to random guessing, so not very successful. It is not too surprising if we just inspect the t-SNE plots generated here. Unlike the ones from predetermined architecture, the t-SNE plots here are very difficult to distinguish for the different custom models, even for the researcher who look at it all days. So considering the various settings that are involved when we plot for the machine learning models, we try to evaluate as many scenarios as possible to show that the method is actually versatile and works well in various scenarios. So here I'll show some of the different settings that we considered. First of all, we can take a look at how color in t-SNE plots affect the attack performance. So overall, the effectiveness remains similar across all 3 settings that we looked at, namely color, grayscale, and binary, where only the location of the data point is recorded. So due to its success, we can say that it is potentially increased the risk of this attack because it is insensitive to the color. And we also look at how different data sets affect the attack performance. Just by looking at different t-SNE plots, we observe that different data sets will yield drastically different t-SNE, even with the same model. So the examples showed here are t-SNE plots from ResNet 50 models that are trained on the 3 different data sets. So first, if we combine the training data from different data sets, we find that the attack did not deteriorate from this combination, so which indicates the attacker do not need to train a separate attack model for each data set. And next, if we look at how the attack generalized across different data distribution, as we've seen, the t-SNE plots are actually very different given different original training data. The attack is not very effective when directly inferring on plots generated from models trained on different data sets. However, if the adversary can just have a small number of in-distribution data to fine-tune the attack model, and the attack performance will quickly improve. So we have results on more settings, such as t-SNE density and perplexity. Please check it out in the paper if you want, if you're interested. So in addition to developing the attack, we also try to find some defenses that can mitigate this risk. We propose several disturbance-based defenses. So there are 2 potential targets and 3 strategies for adding the disturbances. For the 2 targets, we can perturb the embedding before generating the t-SNE plots, or directly on the coordinates on the plots afterwards. And the 3 strategies include rounding by decreasing the fidelity in the data, or thresholding, where we only use larger values in the embeddings to generate t-SNE clusters, and just directly adding Gaussian noises. And we find the most effective defense methods are embedding thresholding and adding noise to the coordinates, which both decrease the attack performance while preserving the plot's characteristics. However, if we consider an adaptive attacker who is aware of these defenses and train the attack model with the disturbed plot, the defenses will unfortunately be rendered ineffective. So that's our results on t-SNE. As we mentioned before, so these loss plots is another widely used scientific plot, and we also conduct some experiment to see if the attack is still effective on a different type of plots. We find our attack can successfully extract the model type information from the loss plot, both with or without the axis information. Similar to t-SNE plots, we propose several disturbance-based defense mechanisms, mainly by smoothing the trajectory or adding noises. And smoothing the curve with sliding window is most effective against the attack while preserving the overall shape. However, in the presence of an adaptive attacker, the defense once again becomes ineffective. So in conclusion, we propose the first model information stealing attack through scientific plots, and from our results, we find it is indeed possible to extract these information about the model from both t-SNE plots and loss plots. And we also propose some disturbance-based defenses that can decrease the attack performance. But before adaptive attacks, it will still remain effective. And that's all for the paper. Thanks for listening. So let me know if you have any questions.